Hello and welcome back to your Chem 4 lecture. We are moving on into chapter 14 with a few different carbonyl compounds and amines that we're going to talk about today in our organic chemistry section. So let's go ahead and get started. So it's just basically doing the same thing we were doing in chapters 11 and 12, where I'm going to show you several functional groups, and we'll talk about how to name those compounds with those functional groups, and then also what reactions they undergo. So starting from carboxylic acid. Now you'll notice here that the carboxylic acid is another group that has a carbonyl on it. Again, the carbonyl is this C double bond O motif that you see on the screen. Now specifically for carboxylic acid, that C double bond O is then bonded to a hydroxyl group, which if you'll recall from the alcohol chapter is an OH group. So we have a carbonyl plus a hydroxyl group. Overall, that is what's called a carboxyl group or a carboxylic acid. And we'll see there's a bunch of, all of these motifs have different chemical properties that we're going to explore in this chapter. Okay, now the good news is we'll start with the easy thing for carboxylic acids, which is how to name them. They're actually fairly straightforward to name. What you do is you take the longest carbon chain that contains the carboxylic acid, and you basically take the IUPAC name for the alkane. So like in this case, we have methane over here. And what we do is we lose the E, so methan, and then we add oic acid. So one carbon carboxylic acid is just methanoic acid. Ethane becomes ethanoic acid. Propane, propanoic acid. Butane, butanoic acid. Pentanoic acid, etc. And furthermore, because the carboxylic acid is a terminal group, it can't be in the middle of a ring like a ketone or in the middle of a chain like a ketone. It has to be at the end. That means the carbon that's in the carboxylic acid is carbon 1, and you number it from there. So in this case, we would number this one 1, 2, 3, 4, and we would see that that was butanoic acid. With a substituent on the third carbon, it's a methyl substituent on the third carbon, so it becomes 3-methyl butanoic acid. Now, there is a special carboxylic acid that we'll need to know because it's aromatic. And this is this one here. It's what's called benzoic acid. Do I have it? I thought I had a special slide on it, but I guess I don't here. So benzoic acid is just a benzene ring with the carboxylic acid attached. Very similar to benzaldehyde. Now, for this numbering scheme, the number 1 carbon is the carbon on the ring that's attached to the carboxylic acid group. And then you number it from there, either clockwise or counterclockwise, whichever one gives the lowest numbering. So this becomes 2,3-dichlorobenzoic acid. Likewise, over here, we have a methyl group on the third carbon, so that's 3-methyl butanoic acid. Okay, now there's literally 2 carboxylic acids that you need to know the common name of because they are in common usage. One for being poison and the other one for being like a relatively common like flavoring agent or something that you can drink anyway. Up top, we have methanoic acid. That's the IUPAC name, but it's usually not labeled that way. If you see it in like a medical setting or a chemistry lab setting, it's called formic acid. Formic acid is a poison. So it's very important that you don't take in any formic acid. But it is useful for other circumstances. So just keep that in mind. Formic acid is a poison. Next up, ethanoic acid is actually known as acetic acid. Now, acetic acid is important because that's the main component of vinegar. So, of course, use it for food, but also vinegar is important for various industrial reasons, like industrial reactions involve vinegar and cleaning agents involve vinegar. It's much less poisonous than formic acid. Although I'm sure if you drink enough of it, you could hurt yourself too. Okay, yeah, I was just kind of pointing it out here. Formic acid, I hope I have this correct, is named after the word formos from the word for ant in Latin. That's because the acid in an ant sting is actually formic acid. So it gets named after the ants. Likewise, vinegar, I mentioned here as well. That comes from acetic acid. So just the main component of vinegar and the thing that's responsible for its taste. Okay, so let's go ahead and do an example name here. Now, I feel like you should probably be able to do this on your own, but if you want some help, we're going to walk it through. So if you feel confident enough to start naming this compound here, go ahead, give it a shot. And if not, we're going to walk it through. So pause the video if you're ready, but you can just stay and stay with me here if you're not. Okay, so first up, we should identify, oh, this is a carboxylic acid. We have a carbonyl here bonded to an OH group here. This is carbon 1, and we go carbon 2, 3, 4, and 5. 5 carbons total would be pentane. Name it as a carboxylic acid, pentanoic acid. Okay, so pentanoic acid is going to be our base name. Next up, we see that we have a substituent. It's a methyl group on carbon 1, 2. So that means it's 2-methyl pentanoic acid. And that's how we can name it. Okay, so go ahead, give it a shot for both of these. Note here, the B here is a benzoic acid again. So just be aware that that's got its own separate naming scheme like we talked about. So pause the video now, go through sample exercise number 1. And when you come back, we'll take a look at the answers. So pause. Okay, so let's go ahead and take a look. So for the left side here, this is carbon 1, obviously. We can count it carbon 1, 2, 3, or carbon 1, 2, 3. Either way works, not a big deal, whichever one you choose. Then we notice we have, so that would be propanoic acid, because it's propane is for 3 carbons, minus E plus oic acid, propanoic acid. And then we have a methyl group on carbon 2, so that's 2-methyl propanoic acid. Over here, we should recognize it's a benzene ring with a carboxylic acid group attached. And we note that we have a bromine on carbon 1, 2, 3. So that should be 3-bromo benzoic acid. Remember, carbon number 1 is the one that's attached to the carboxylic acid group. This is not numbered in the benzoic acid scheme. Okay, now why don't you try to draw a line angle structure for 4-chlorohexanoic acid. Pause the video here, and this time we're going from the name to the structure. So take your time, and when you come back, we'll take a look at the answer. So pause. Okay, let's take a look at the answer. So the line angle formula, what you want to do is, okay, it's hexanoic acid. That means it's 6 carbons long. So you go 1, 2, 3, 4, 5, 6. And you choose either side. I mean, here we're going left to right, so we might as well choose this one as the right side. And we draw in our carboxylic acid group, that's a double bond to an oxygen, and an OH group, a single bond to an OH group. Okay, so there's our hexanoic acid. Next up, we have a chloro group on carbon 4. So count it over, 1, 2, 3, 4. We have a chloro group on carbon 4, which we can draw just that way. Okay, so again, if you have any questions, make sure to ask them in the comments down below. And this will be on the worksheet for lab as well. So carboxylate salts, so we're going to talk about carboxylic acids now and some of the chemical properties that we see, because we actually are commonly interacting with carboxylate salts and carboxylic acids all the time. Okay, so the first most important property of carboxylic acids is that they are very polar. Basically, the combination of a carbonyl group with an OH group means that you have 2 different very polar groups that both lead to a strong polarity in this molecule. Again, you have partial negative charges on oxygens and partial positive on the hydrogens and the carbon that's in between. So because of this, carboxylic acids can hydrogen bond with water molecules. And so that means that a lot of them are going to be very soluble. So carboxylic acids that have 1 to 5 carbon atoms are going to be soluble in water. Now, as you increase the number of carbon atoms, you increase the number of nonpolar groups. So the solubility of the carboxylic acid will reduce as you get to 6 and more. But for the purposes of this class, we're going to say that 1 to 5 carbons with the carboxylic acid are soluble in water. Hexanoic acid is slightly soluble, meaning that some of it mixes in. But again, for the purposes of this class, we'll just call that insoluble. Same thing with benzoic acid. Benzoic acid will dissolve a little bit in water, but we will just call it insoluble for the purposes of this class. Okay, now, carboxylic acids, in the name it says acid, right? So that tells you right away, this is going to be an acidic compound. And these carboxylic acids are indeed weak acids. Acetic acid we talked about a lot during the weak acid chapter, because we talked a lot about how acetic acid ionizes partially in solution to produce whatever carboxylate ion you form and a hydronium ion. So let's go ahead and take a look. So carboxylic acid, that's this group right here. Now, this proton here on the OH, that's the proton that's acidic. So this one gets donated from the OH group to water, forming the hydronium ion. And that leaves you with this group here. Now, this group is, obviously very closely related to a carboxylic acid, but notably it doesn't have a hydrogen here. It's got a negative charge on one of its oxygens. This is what we call a carboxylate group. So this carboxylate ion here basically has a very stable negative charge because the negative charge is actually shared between the two oxygens here. Okay, I think we're going to talk about how to name it here, but we can go ahead and mention the naming scheme now. So note here, this is ethanoic acid. When you remove a proton and you form the carboxylate ion, to name it, what you do is you subtract ic acid and add 8. So ethanoic acid, when it loses its proton, becomes the ethanoate ion. That's better known as acetate. So acetic acid becomes acetate. Okay, so let's go ahead and give a shot here. Sample exercise number 3 says, write the balanced chemical equation for the dissociation of butanoic acid in water and identify the carboxylate ion. So go ahead, if you start from butanoic acid, write the dissociation equation, just like what you see here, and then give me the name of the carboxylate ion that forms. So pause the video now, give it a shot, and we'll walk it through when we come back. Okay, so you're given the fact that you need the butanoic acid, or you're given that you have butanoic acid and water. They're going to react to form the carboxylate ion that forms, the so-called butanoate ion, and the hydronium ion. So the way that you can draw it, and I recommend drawing it line angle structure, but you can also use the condensed structural formula like this if you prefer. So here we have the carboxylic acid reacting with water. It's going to donate a proton that forms the hydronium ion. And then that leaves you with the carboxylate ion that's right here, where again, we have 4 carbons and this carboxylate functional group here, which is a carbon double bonded to an oxygen, single bonded to an oxygen that has a negative charge because it's missing its hydrogen. Now, normally we don't just focus on the carboxylate ions in solution. You can actually form carboxylate salts by reacting a carboxylic acid with a base. So if you take a carboxylic acid and react it with sodium hydroxide or potassium hydroxide, you can actually get a salt of the carboxylic acid. So here, if we take formic acid and react it with sodium hydroxide, what happens is the proton from the carboxylic acid reacts with the hydroxide group to form water, H2O. And that leaves us with a cation, sodium, and an anion, which is the carboxylate ion, in this case, methanoate or formate. These are often used as flavor enhancers and also as preservatives because they basically keep the pH high and that can reduce the amount of bacteria that can grow. Okay, I already mentioned this here, but the carboxylate ion is named by replacing the ic acid with 8. So benzoic acid becomes benzoate, for example. And then the way that you name the salt is just use the cation name followed by the anion. So here, benzoate being the negative charge, that's our anion. Potassium in this case from potassium hydroxide is our cation. So we call the salt between potassium and benzoate just potassium benzoate, just like we named those ionic compounds, so long ago this semester. Okay, so carboxylate salts themselves are ionic compounds. They're solids at room temperature and they have high melting points. However, usually they're soluble in water because you have this strong negative charge here and a strong positive charge here that both want to associate with water. A famous carboxylic acid salt that's used in a lot of cooking is what's called monosodium glutamate, or MSG. This is glutamate here. It's a relative of glutamic acid, which is an amino acid that we're going to talk about very soon, I think in a couple chapters here. And if you just react one equivalent of sodium hydroxide with it, you get this monosodium glutamate, which acts as a really good seasoning agent for like umami flavor. What else do I want to say? Yeah, so it's just a solid at room temperature, high melting points, and soluble in water. So some of the ones that are used are, for example, sodium propionate, or propanoate is what we would call it. And that's cheeses and breads, frequently used as a preservative. Sodium benzoate inhibits growth of mold and bacteria, is frequently used for fruit juices, margarine, relishes, salads, and jams. And then finally, MSG is a flavor enhancer, which gives like a umami flavor. Okay, so go ahead, give me the balanced chemical equation for the reaction of propanoic acid with sodium hydroxide. Now, in this case, you're given propanoic acid and an NaOH. It's going to be a neutralization equation, which means that you're going to form the carboxylate salt and the water. So go ahead and pause the video here and give it a shot. And when you come back, we'll take a look at the answer. So pause. Okay, so I'll assume you paused. Let's go ahead and take a look. So what happens is the carboxylic acid is propanoic acid. So that's 1, 2, 3 carbons with the carboxylic acid group. Reacts with sodium hydroxide. Now the hydroxide and the proton from the carboxylic acid are going to react together and form water. That leaves you with the sodium ion as your cation, and then you have this negatively charged carboxylate group. So propanoic acid becomes propanoate. So the combination of those in salt becomes sodium propanoate. Okay, so we also want to link this to health as well. And one of the key things to understand is that carboxylic acids are part of our metabolic processes. Basically, the way you can think of our metabolism, and we'll cover this in a future chapter, is that basically what we're doing is we're slowly breaking down carbon by carbon, all of the carbons that are in these longer chains. And one particular example is the reduction of pyruvic acid to lactic acid. Pyruvic acid here has 2 carbonyls in a row, and the second carbonyl is a carboxylic acid. With 2 equivalents of hydrogen from a biological source of hydrogen, like NADH, you can form lactic acid. And lactic acid you may have heard of before. Normally, glycolysis leads to a molecule of glucose breaking down into 2 molecules of pyruvate. That's the carboxylate of this one. However, during very strenuous exercise, when you don't have enough oxygen in your muscles, pyruvic acid can be reduced to give lactic acid and the lactate ion. Now, this is not your body's #1 form of it, so you end up with buildup of lactic acid in the muscles where the oxygen needs to get to. And that's actually what causes soreness in your muscles, is a buildup of these lactic acid and lactate molecules. Sorry, so we're going to talk a lot about this metabolism in the future. So this is like a little taste of what's going to come. In the citric acid cycle, which is better known as the Krebs cycle, we have di and tricarboxylic acids, and these are decarboxylate. Basically what happens is you take off one part of the chain here, and by oxidizing it, and you basically slowly unzip the compound, unzipping the carbon-carbon bonds as you go along and releasing carbon dioxide. So the start of the citric acid cycle starts from, of course, citric acid. And what happens is you take your six carbon citric acid and decarboxylate it to produce alpha ketoglutaric acid. Decarboxylation means the carboxylic acid group is actually removed. In this case, this one here is removed, and you lose a whole carbon from your carbon chain. Now, in the future, we're going to talk more about this. Alpha ketoglutaric acid then decarboxylates again to give succinic acid, which is here. Then you have a series more of these decarboxylation groups here. You don't have to memorize this for the test or anything, but it is just relevant for the future. So you take succinic acid, goes to fumaric acid, goes to malic acid, and then finally oxaloacetic acid. So yeah, these functional groups that we've been studying, they're all going to be involved in metabolism that we're going to study in our future chapters. Oh, okay, well that does it for today's, for this lecture, lecture 31. We're going to talk about esters in the next one. So make sure if you're feeling good, just move on into the ester lecture, because we're going to pick up right where we left off. Until then, I'll talk to you soon. Bye-bye.